20, I'm just going to take the rigid wall device all the way down. There's the rigid wall. We have an opening at the bottom on which the geotextile is mounted. And then we can conduct either a falling head or a constant head device, much as we would do for soils. The differential head across the system is going to be from the water level controlled by the outlet. On the inflow, this is where it's essentially acting as a constant head, isn't it? You know, you've got your inflow and you're controlling the elevation of the water level on the upstream side. You're actually controlling the water elevation on the downstream side because of the overflow here. And so the distance between here and here is going to be the head that's driving the flow. We can measure the outflow, Q. That outflow is happening because the water's come down through the geotextile and across or out through the system. The geotextile has a finite thickness. Let's go in and acknowledge that. There's the thickness, and it's the thickness of the geotextile. And then knowing the cross-sectional area of the test specimen, that's actually going to be through the orifice here. We pretty well have everything that we need to determine a hydraulic conductivity normal to the plane of the specimen. So let's look at this as a Kn, a conductivity normal to the geotextile. Schematically, I've drawn two layers here. Actually, that's a fair point. Sometimes people will stack 2, 3, or 4 geotextiles together. I've seen that done. Let's the one layer, okay? And that hydraulic conductivity, K sub n, is equal to Q multiplied by the thickness of the geotextile divided by the cross-sectional area A and the differential head H across the system. The H over GT is giving us the hydraulic gradient. And that's often expressed and reported by manufacturers and picked up in the Canadian Foundation Engineering Manual as a permittivity. So we'll probably see that reported as a value of permittivity. Thus, the units are a little strange. Seconds to the -1 is equal to Kn divided by the thickness of the geotextile is equal to Q A over H. And let's just leave that there for now as a definition of permittivity, the permittivity of the geotextile defined by this value here. We're not going to get too excited about this. It's an index test, and it's used almost as a screening tool for filter applications. If we're going to get serious about filter design, we'll actually carry out a separate test, I'll speak about it shortly, where you would put soil in combination with the geotextile and flow water through the soil geotextile combination, not so much in an index test, but in a performance test, okay? Let's move to the second of these two index tests, and we gain, I think, a nice insight both to soils and geotextiles, or well, you could do a transmissivity test on a geotextile. You could also do it on a geonet, and I'll speak to the geonets as my primary vehicle to make a particular point here. Okay, so what are we doing? We're taking either the geotextile and placing it in red, wouldn't so commonly be measuring the transmissivity of a geotextile, but you could do it. More commonly, measuring the transmissivity of a geonet. So there's the geonet in planar form, and we would put it into a device that can cause flow in the plane of the material, of this porous medium. And in this case, we can measure what's termed the transmissivity. And the transmissivity T, it's going to have units that, again, are a little, at first you think, wait a second, how does that work? But bear with me. The transmissivity T is equal to the in-plane hydraulic conductivity times the thickness, let's call it the thickness of the geonet. So now let's go in and acknowledge the thickness of the geonet or the test specimen. Boom. Okay. We have the width of the test specimen from this image, and it's a shame that both textbooks and standards don't quite capture everything exactly, but the differential head across the system here is now delta small h, which, to tell you the truth, is exactly the same thing as the big H here. I've used this because that's how it's appearing in the Canadian Foundation Engineering Manual. So bear with me, but let me just point that out to you. Unfortunately, that's the way it is. And once again, we'd be measuring the outflow Q through the system. Okay. And the transmissivity would be given by QL delta H multiplied into W. Okay. So we'll have manufacturers report a transmissivity, or we'll have manufacturers reporting a permittivity. Largely index tests for relative flow rates. If we were to move to a performance test, we'll speak to those shortly in the context of filter design. But let me present some data for you coming from transmissivity testing. It's actually transmissivity testing we did a number of years ago at UBC. And the reason for doing this is actually to get to the data over the page. The data over the page are actually for flow through more porous soils. There's a 3/4 inch gravel. And so what I'd like to do is to map the nature of the flow regime and flow quantities through a GNet onto data for soils and thus gain an appreciation. That's our target, is actually to finish here, but we need some data for GeoNets to add to the data for the soils, which are actually taken from Cedergren's book. So what are we looking at here in the way of these data? And let me see if I can split this up. There's transmissivity test data, and they've been performed at various normal stresses. So let me go back to this image here and put on a normal stress. Okay, so let's give that sigma. And that sigma is the sigma that we're seeing here. Okay, so now we'll go in and say sigma and KPA. And we have sigma, and the tests have been run in a number of stages. In fact, it's a suite of tests all pulled together. So sigma is held constant, and the flow is measured. So let me go back to this page here. Let me hold sigma constant. Let me hold sigma constant at 25 kPa. And now I'm going to measure the flow rate Q for various differential heads across the system or hydraulic gradients. Okay, the hydraulic gradient I, we'll go back to the previous page. By inspection, the hydraulic gradient I is going to be delta H over L. So here we have Q, the hydraulic gradient delta H over L, as a function of sigma, initially held constant, and the hydraulic gradient stepped up. Let's follow the emerging story. So we have data for I equals 0.02, I equals 0.04. These are relatively small gradients, 0.04, 0.06. Oops, bear with me. 0.08 and 0.1. Okay, and by inspection, we can almost see where we're going to be heading with in an observation on these data. We can see that all these lines are getting a little bit closer together here. In other words, if we double the gradient, we couldn't quite double the flow. If we double the gradient again from 0.04 to 0.08, we don't quite double the flow. Okay, so we make an observation in these flow data at a normal stress of 25 kPa, which is not that much, right? It's about a meter of soil or so sitting on top of the geonet. We observe that if we double the gradient, we don't double the flow rate, and thus it doesn't look like Darcy's law is holding true. If we increase the normal stress to 100 kPa and reimpose that sequence of hydraulic loading, we notice that the flow rate has dropped a little bit, and in fact we see by inspection is fairly quick and arguably maybe a little bit more time dependent after that. Depends how much we really want to try and read into these data. But let's up the normal stress again, 200 kPa. Let's up it again, 300 kPa, and indeed let's up it to 400 kPa, which is beginning to become a sizable surcharge load on through the platen, 400 kPa sitting on top of the specimen. And we're continuing to flow water through it. And can you imagine the specimen has a finite strength in compression, be a function of the density of the geonet, and this is a so-called medium density geonet, but it'll have a crushing strength, and it would appear that we're beginning to perhaps get close to that crush strength. If I remember correctly, it was in the range about 500 to 600 kPa was the crushing strength of the material. Okay. Now, I'd like to pursue this flow regime. So that's going to take us back to these data. The data at relatively low stress. I could do the same thing at the higher stresses, but we can go through and analyze these data at the lower stress. Let's observe that with sigma increasing, Q is going down, and Q is going down because the pore space essentially is diminishing. Okay. Now, if we come back to the flow data, so now let's say let's examine the flow regime in the GeoNet. And if I was to say why, I'd say for two reasons. Reason number one is to determine Darcian or non-Darcian and to find the evidence in support of that claim. And reason number two would be what's the equivalent porous medium if it was to be a soil? Is it a fine gravel, a coarse gravel, coarse sand? What's the equivalency of this GeoNet? And for that, let's start with the flow regime at I equals 0.02. And let's assume that's laminar flow. Let's assume that this 2% gradient is so low that the nature of the flow regime is essentially laminar or as close to it, okay? So let's do that. We'll acknowledge here, assume laminar flow. Perhaps we'd have to drop it as low as 0.01, but let's assume it's laminar flow. Then we can say Q is equal to KIA if we were to look at it as Darcian flow. And what is that flow rate? That flow rate is about 30 milliliters per second. Let's look at 0.06. What is Q? Q is equal to, now we're postulating that the equivalent hydraulic conductivity is diminished, that it's compromised by semi-turbulent flow. So I'm going to give it a different K. I'm going to call it K prime. We know what the hydraulic gradient is, we know what A is, and the flow rate at 0.06 is, let's call it 58 milliliters per second. And then at the hydraulic gradient of 0.1, again, I'm going to give it a different. I'm going to look at these ratios of hydraulic conductivity. So the K is denoting Darcian permeability, and the K prime is a non-Darcian permeability. And we have at 0.1 ballpark, let's say 75 milliliters per second. So if I go through and I look at the flow rate at the I equals 0.02, or I look at K, I'm going to get that K is equal to 30 over 0.02 times A. Q divided by IA. If I go in at the 0.06, or even let me go in at the 0.1. If I go in at 0.1, let's do that. I'm going to say that K prime is equal to 75 0.1 multiplied into A. Okay, and therefore I can look at the relative permeability. Right? Let's take these out here. I can look at the relative permeability, and I'm going to say, you know what, K prime over K is equal to, and if I divide it through, it's going to be 0.5. Let me just let me say about 0.5. Now, let's take those insights over the page. Okay. We note that Q is stress dependent. So the relation that we've got here is holding true for the effective stress or the surcharge pressure that we've been looking at it. But if I take it over the page, then I can look at this relative K. K prime over K is the relative K. In Cedergren's book, he gives it a constant C. And he has data generated for various soils here. Let's take a look at those soils. Okay. The 0.025 inches is about 0.6 of a millimeter. If we chase it through, 0.5, half inch, 12.7 millimeters, 0.75, 3/4 inch minus, 19 millimeters. Then we got the 1 inch and the 5 inch. Now I'm going to highlight these ones here. So let's look at this. Let's capture those curves. Okay. Because if we look at the way in which these data have been generated for soils, rough guide for estimating reductions in the hydraulic conductivity of narrow-sized, uniformly graded aggregates as a consequence of turbulence or semi-turbulent flow. It's preliminary guide only. It's from flume tests that Cedergren reported. I don't know where the original data come from, but they're reproduced in his textbook on various flume tests on crushed American river gravel, constant head tests on graded Ottawa sand. So we've got combinations of the gravels, it's flume testing on the gravels. And what Cedergren did was to assume laminar flow at 0.01. So there's a hydraulic gradient of 0.1. At 0.01, we would be down in here. So perhaps I'll do that here. Because this is the gravels down here, so the sands and the gravels. So at about 1/10 of that, let's go in here. Okay. And these data here, right? See the 3 sets of data. So the initial values here are assumed laminar flow. At 0.01. That was the lowest gradient that Cedergren's data had imposed. The lowest gradient that we have for the GeoNet data are 0.02. But Cedergren did exactly the same thing. He looked at the relative reduction, the relative K, and the data are plotted here. Look, there's I think that's the Ottawa sand, and then the 0.3, 0.4, and 0.5 inches are the crushed American river gravel. And if we come in and, excuse me, plot the GeoNet data, then we've assumed laminar flow at, actually, let me add one additional qualifier. I suspect these data are actually at a gradient of about 0.02. I suspect that 0.01 has to be, because all these all these curves are coming up to here. That's the 0.01. Excuse me. So these data are acquired at 0.02, and looks like this is 0.05. So these are various gradients, but all the data points are coming up to a unique point here. In our case, we would have an assumed, for the GeoNet, I can't quite get it in, but let me attempt. We're assuming, let's say, assume laminar flow soils data. And we're assuming, just to be thoroughly consistent, we're assuming laminar flow at 0.02 for the GeoNet data. Okay. But if we go out to a hydraulic gradient of 0.1, which are the data that we have here, 0.1, our relative permeability ratio, K prime over K, is 0.05 for the GeoNet data. That's what we're seeing here. And if we go out and impose those GeoNet data at 0.1, we have a relative hydraulic gradient of about 0.5. So that data point there is from the GeoNets. K prime over K is approximately 0.5 at I equals 0.1. Okay. And in fact, we could go in and do it for the ratio of 0.6 as well. I think the number comes out. Let me check my my calculations. You could probably do the same. I get about 0.64. I get a ratio of about 0.64 for the ratio there. And we could draw essentially what would be the relation or the curve for the GeoNet data, and it's going to plot something like that. So what do we see here? And it's something that's of interest to us both for soils as well as for geosynthetics, is we have non-Darcian flow. To maintain Darcian flow, the relative hydraulic conductivity, C would equal 1. Okay. As the hydraulic conductivity as the hydraulic gradient is increased, the hydraulic conductivity wouldn't change as a consequence of the hydraulic gradient. So the fact that everything is dropping off here, so for 3/4 inch gravels, there's non-Darcian flow. For 1/2 inch gravels, there's non-Darcian flow. The relative hydraulic conductivity at a gradient of 0.1 is about half of that at a gradient of 0.01. And that reduction is because of energy losses in the semi-turbulent flow and the streamlines no longer being parallel. And we see two things. First up is this reminder that not all soils exhibit Darcian flow. Indeed, if we went back and looked at the data here, this would imply if the grain size is much greater than about 0.5 millimeter, you're going to entertain not a major impact, but you're going to entertain some element of non-Darcian flow. So we see non-Darcian flow in soils. 3.8, let's call that 4 millimeters. Here we're getting at about the division between coarse sand and fine gravel. Okay, so gravels exhibit non-Darcian flow. And the geonet behaves like a gravel. In fact, it behaves like a gravel. It's something like, in terms of its hydraulic regime, the nature of the non-Darcian flow in the geonet here is equivalent to the non-Darcian flow in about a 1/2 inch to 3/4 inch gravel. And were we to cast our minds back to this page a little earlier in the notes, do you remember this one? The laminar flow, the transition into turbulent flow in pipes, laminar flow in soils, but not all soils. And this chart was implying that the transition from laminar flow to semi-turbulent flow was occurring at a D10 of about 1 millimeter or so. These data are implying that the semi-turbulent flow is kicking in, let's say, by and large, in and around 1 millimeter. So it's not a bad number to consider the grain size at which you would say, I'm mindful it's non-Darcian flow. Whether or not that's going to make a big difference would depend on the hydraulic gradients that you're looking at. Okay, so that's what I wanted to do, these data, and it was the reason for looking at transmissivity is that we have non-Darcian flow. At elevated hydraulic gradients. So that's the first point to acknowledge on the geonets and flow through geonets. And there's a second point I wanted to make here is just because water can flow through it quite easily, here was another series of data acquired at that time, and the data are they include, look, they're being acquired at a stress of about 300 kPa, sigma equals 300 kPa, I is equal to 0.02. So let's go back up to here. Sigma is 300 kPa, I is about, 0.2. So that would be this set of data. The flow rate is about 20 milliliters per second. And those data are actually the data that are imported here. In a separate test, it's just giving it's the same flow rate. But in this case, this stress has been imposed, this hydraulic gradient imposed, and the flow measured over a longer period of time. In these tests, the stress was increased every 24 hours. In these tests, the stress was held constant, in contrast to here, and the flow rate measured over a longer period of time. So these data are literally just showing that they're consistent. Maybe that it's not so much that they've been exported, but there's consistent observations. I'm not quite too sure why these don't go back all the way to 0, but we'll leave that as it is. And then the other data are for leachates. And various geomembranes of, there's a number of different geomembrane products in here. And all of those geonets with the leachate flowing through them, the flow rates all drop to 0. It was complete clogging with the biomass. A combination of physical, chemical, but primarily biological clogging. So I want to just to draw your attention to the fact that all materials, gravels included, and we'll see this when we get to barrier design and field performance data reported by Kerry Rowe in his Rankin lecture, the potential to clog materials always exists, notwithstanding their transmissivity or flow capacity in water. Okay, so quick summary. We've been looking at cross-plane permittivity as an index value. We've been looking at transmissivity as an index value, but I actually elected to use the transmissivity test to examine the nature of non-Darcian flow regime in the very porous materials, such as geonet, and acknowledge that non-Darcian flow is also present in the equivalent porous graphels. Okay, so that's how I want to park this for now and acknowledge two things. We'll come back to look at this cross-plane permeability in geotextiles with a soil in combination with it. But in advance of that, let's take a look at cross-plane flow regime, but do it for a geomembrane. Okay. Now, if I gave you a bit of a schematic here, let me try to do this in the following way. I'm observing that we have a Darcian flow primarily in sands. Let's put, because I want to move to the non-Darcian flow kicking in the coarse sand. So let's put medium sand. Let's put coarse sand and gravels. Then let's have the silts. And now let's put the clays. Bridging across into non-Darcian flow. If we have very low permeability clays, observations of Darcy's law being applicable also break down. So Darcy's flow is describing a sweet spot or Darcian flow is occurring in a sweet spot of porous media that in which the flow regime is laminar, okay? Breaks down with very coarse porous media, breaks down with very, very, very fine kind of non-fissure clays. And I'm going to map onto those now that we have geotextiles with Darcian flow, we have geonets with non-Darcian flow, and we have geomembranes with non-Darcian flow. And so the purpose of this is just to acknowledge the nature of the non-Darcian flow in geomembranes, and I'll do this with in two ways. Let me find a data sheet for a geomembrane, and if we look for something that's going to speak to its cross-plane permeability, we get something called water vapor transmission. What is water vapor transmission? Water vapor transmission is a test method, and this is our materials testing, a test method in ASTM, and it in turn is recognized in another ASTM document 5886, Standard Guide for Selection of Test Methods to Determine Flow Permeation Through Geomembranes for Specific Applications. Okay, and the essence of it is captured here. Geomembranes are non-porous homogeneous materials, and in the words of ASTM, thus the nature of the flow across the plane of the geomembrane, we've got absorption or dissolution on the upstream side. We've got diffusion. It's a diffusive process. It's not advective flow. It's diffusive flow. And then desorption on the downstream side of the barrier. And that, in essence, is the nature of the flow regime as captured by this water vapor transmission, grams per R per meter squared. Okay, so let's just make an acknowledgement of that. So if I were to speak to that, how would we capture that? In essence, you're going to drive the transport across the geomembrane. Let me take the geomembrane here. Let me pop the geomembrane on. I'm going to put the geomembrane over a container, and I'm going to seal the container. And I'm going to place some water in the sealed container. Okay, with the geomembrane on top of it. And there's the geomembrane. And I'm going to create a flux of water vapor across the geomembrane by controlling the humidity in a chamber outside. Let's argue there's the chamber, and the chamber has controlled humidity. So I'm now going to have a flux, and I can measure the flux if I place the system on a scale. Okay, and then I can look at the change in mass that's occurring across the cross-sectional area over a period of time. And those observations of water vapor transmission are going to give me my grams per R per meter squared. I'm not going to pursue it much further because, in essence, when we do have flow across geomembranes, flow of water across geomembranes or a fluid, it's nominally dominated by holes or imperfections in the geomembrane. And so we'll visit this whole issue of flow through barrier systems in the context of barrier design. I simply wanted to acknowledge, and it's more for the contrast, that we have non-Darcian flow, very, very low flows for the non-porous geomembranes. We have, ironically, non-Darcian flow in the very porous geonets. And the Darcian flow is occurring somewhere between. Now, I could almost choose to cut this discussion on materials testing at this point, but I wanted to introduce two additional tests. There are a myriad, so I'm selecting because they'll be relevant to the design applications. Okay, so let me return to give a brief overview, and bear with me, I appreciate going through materials testing and test methods doesn't exactly set the world on fire. But do you remember I said, look, here's this permittivity. It's a bit of an index test. It's really just a screening tool. It gives us a, a relative value between different materials. But what if you took this rigid wall permeameter? So I'm going over the page. I think this is the penultimate page of your notes. What if I took the permeameter? Let me keep the rigid wall permeameter. So I'm going to do that. Let me, here's the rigid wall permeameter. Again, we'll acknowledge the presence of measuring ports, but in essence, this is the bit that's the rigid wall. Okay, so that is analogous to that. Let me put the geotextile in there. There's the geotextile. There's the geotextile. So now that is analogous to, here's the rigid wall, geotextile through which the water is flowing. There's the rigid wall, geotextile across which the water is flowing. Let's put the flowing water. Water inlet. Water is flowing down. Water outlet. So everything so far is analogous to this permittivity test or cross-plane permeability. But what then if we were to place soil? A soil specimen. What if we were to reconstitute a soil specimen and actually flow the downward unidirectional seepage flow? What if we were to flow water across that? Okay, and that's what's referred to as the ASTM gradient ratio test. I'm not going to go into too much detail for reasons that will become apparent, but I want to give you a sense of the basis for its interpretation. Okay, so if we give it a name, it's the ASTM 5101. ASTM 501. Now we've got to come up with some way of characterizing it. It's no longer an index test like the permittivity. It's now a performance test, or at least a performance-oriented test. And in essence, we have the ability, by tapping manometer ports or putting a differential pressure transducer across them, and we can measure a differential head, right? If we measure a differential head and we know the distance between the tapping points, we can get a hydraulic gradient I. In fact, we could measure it on both sides of the permeameter to get a redundant measurement of a gradient I. And in fact, if we have other manometer ports, and let's look, there's one shown here, where we to put a differential pressure transducer across here, we could get another hydraulic gradient. Okay. This hydraulic gradient is within the soil. So let's call that IS for the soil, IS for the soil. This one is across the last little bit of the soil and into the geotextile, across the geotextile. That's across the soil geotextile composite, I sub G. And the gradient ratio, it's a ratio of hydraulic gradients. So if we look at this in terms of a gradient ratio, we can look at the gradient ratio ISG over IS is really a hydraulic. It's actually the hydraulic gradient, because we call it the gradient ratio test. The gradient ratio test. Now, in the perfect world, let me take the green box out here. In the perfect world, I'll take the green box out here. I'll put the geotextile on the bottom of it. Okay. In the perfect world, we would have a uniform head loss across the soil, and that head loss would be unchanged by the presence of the geotextile, right? If we were to look at this as this is the distance above the base of the geotextile, and there's the magnitude of the water head. Remember, we're measuring differential heads, but there's the water head. We can give that centimeters or meters of water. Let's give it meters of water. Here's the distance above the bottom of the geotextile. And in essence, this is the hydraulic gradient, delta H over delta L. And if the soil is perfectly homogeneous, it'll be a uniform gradient. And if there's no piping, no clogging, the geotextile is unaffected, it's not influencing the nature of the flow regime, in the perfect world, the hydraulic gradient would equal 1. So we could go in and do that. If, on the other hand, we had clogging going on, the geotextile is filter incompatible. For some reason, we get clogging in and around the zone close to the geotextile. Were we to get clogging, then a lot more of our waterhead is going to be lost in this lower portion. It's going to look something like this. In the presence of clogging, a much greater percentage of the waterhead is going to get lost in the zone of clogging relative to what's behind. So clogging is going to drive the waterhead distribution like this. And the gradient ratio, which is the hydraulic gradient in the soil geotextile composite zone, which is this lower portion here, ISG, the ISG is going to be much larger than the I sub S. So the gradient ratio is going to be significantly greater than 1 in the presence of clogging. Conversely, the gradient ratio will be less than 1 in the presence of piping. Not that much less than 1, because the hydraulic conductivity is not going to change percentage-wise too much. But were the hydraulic gradient to be less than 1, I'll draw it in a slightly exaggerated way, but were we to have a more permeable zone, the hydraulic conductivity, the hydraulic gradient will be relatively less. So our perfect world of a gradient ratio of 1, let me put that through there like this. That's our gradient ratio of 1. And a gradient ratio less than 1 would be indicative of piping. And whether we have piping or clogging is a measure of soil geotextile filter compatibility. Okay. And we can see that in the following, okay? So if the, and these would be my closing comments on this filter or hydraulic compatibility testing, okay? How am I going to clog a geotextile? I could clog it chemically, biologically, perhaps, but maybe in effect, I'd clog the whole system and it was shut down. Or I can clog a geotextile just the way I could clog a filter in a dam, for example. I could clog it physically. Okay. And the following two images are just intended to show you the manner in which gradient ratio testing, in the absence of chemical or biological clogging, can detect physical clogging. Okay. And the easiest way to physically clog a geotextile is to make it quite tight. So let's look at some data now. These are the soils. I'll put the soils in the box here. And the testing was done with each of these different soils in combination with a geotextile. And the geotextile was a non-woven geotextile. Non-woven geotextile with an opening size. It was actually measured according to the Japanese system, which is not quite AOS, so I'm just going to put approximately 70 microns. Okay. In fact, we could go in and mark that on the 190, 80, 70. The non-woven geotextile has an opening size of about 70 microns. So the soils here become increasingly gap graded as we move from across the samples here. And what we observe, we could look at how gap graded the soils are in terms of their ratio of D85 to D15. So the ratio D85 to D15 of the soil. That ratio we can plot down here. And the gradient ratio is plotted on the y-axis. And these seepage tests were run with downward flow through the soil across the geotextile. We have the option as to where we locate this particular port, and it's probably difficult for you to see it, but were I to turn this way, there's actually 25 millimeters is the distance there, or 1 inch. So we can go in and label GR25 is the gradient ratio if the soil geotextile composite zone is measured at a distance 1 inch. And that has changed a little bit in standards, and we won't worry about those details. Point being, we can take this GR25 and acknowledge there's the GR25, which is really just a gradient ratio. ISG over IS, which is really just a measure of, as the gradient ratio increases above 1, it's because we're getting clogging. So as the gradient ratio increases above 1, that would be perfect filter compatibility. And as the gradient ratio increases above 1, we would attribute this, this increase to clogging. And in this case, we're going to attribute it to physical clogging. To physical clogging of the geotextile. And what's causing that physical clogging of the geotextile? It's because of the fine fraction being mobile in the gap-graded soil, but it being caught by the geotextile because most of the finer fraction, most of the mobile finer fraction in the gap-graded soil comprises grains that are smaller than the opening size of the geotextile. So if you like, it was almost like it was the geotextile was always going to physically clog if that finer fraction became mobile. Attributed to physical clogging of the non-woven geotextile by finer, and actually because these fines are less than 75 microns, we could even go in and say it's not just the finer fraction, but it's by fines. Okay. Now I wanted to spend a little bit of time going over this, because in the world of filter design and in bigger projects and in a case study that we'll look at, which was the case study of the rehabilitation of a dam spillway, the owner required that geotextile soil compatibility testing be done. The owner was BC Hydro, is BC Hydro. And so it's not it's a possibility, and therefore the premise or the rationale for interpreting or quantifying filter compatibility is one that we need to understand in advance of going to this case study. Okay, so interim summary, and then I'm going to make a closing remark on the next page. We can test for soil geotextile filter compatibility by carrying out a rigid ball permeameter test, just as we would do to get the index permittivity, by reconstituting soil in contact with the geotextile, imposing unidirectional flow in a downward direction, measuring the hydraulic gradient across the soil and across the soil geotextile zone, measuring it across the soil and the soil geotextile zone, examining that ratio, recognizing that the ratio will be identified by the exact location of this port upstream of the geotextile, and that ratio of hydraulic gradient can be used to characterize whether or not we have clogging, because the gradient ratio will go greater than 1, whether we have piping, because it'll go less than 1, or whether in fact the materials are very compatible. Nominally, the gradient ratio would remain at 1. And were I to illustrate that concept, then you see it here for physical clogging by fines that are smaller than the opening size of the geotextile in testing here. And there's a second test, and it's the last page of the notes. There's a second hydraulic compatibility test. It is the, where I gotta get my page. And that second test moves from a rigid wall device, such as we see here, to a flexible wall device. So let me try to capture that. I'm going to take this, and I'm going to bring it down to here. Now I'm going to schematically show the flexible wall, not a rigid wall permeameter, but a flexible wall. We still have the geotextile specimen on the base, and we still flow water down through the soil and across the geotextile. Let me put the soil, or acknowledge the presence of the soil here. In this case, I'm not going to go into the details of the interpretation, nor am I going to show you test data. I'm going to leave it that this particular test, and let me give it an ASTM code. .5567 is the hydraulic conductivity. It's going to be another ratio, the hydraulic conductivity ratio test. Okay, so it's not a hydraulic gradient ratio, it's a hydraulic conductivity ratio. And that's defined, and this is, we'll park it at this point, that hydraulic conductivity ratio is defined as K through the soil geotextile composite over the initial value, the end of test value over the initial value, which is given SGO, end of test value and initial value. Obviously, we can't go in and do any individual manometer tappings as we did on the rigid wall, right? But we can't do that because the device has a flexible wall. People have tried that and they didn't really have much success. Now, I park that because the hydraulic conductivity ratio test was also run on that spillway project. So now we have to acknowledge the amended. It's flexible wall, recommended for relatively lower permeability soils. For soils with a hydraulic conductivity less than or equal to, it used to be expressed in terms of permeability. I think it's also now also reported with regard to if the soils have a plasticity index. If they have any kind of plasticity, which is implying again they're pretty fine grained, then run this flexible wall. Has the attraction, of course, that you can back pressure the system, for example, and test the soil saturated. In principle, it's probably a nicer test because the gradient ratio test, you can't back pressure the soil, and that's a bit of a limitation, arguably, for it. So how do we leave this index testing for cross-plane permeability? You get only the geotextile, nothing to do with the soil. It's really a screening tool, not of much use to us. If you're on a project and you actually need to examine soil geotextile filter compatibility, which was the case on that hydro project, then you do want to be testing the soil in combination with the geotextile. You can do it in a gradient ratio test. You reconstitute a partially saturated soil, flow water through it, and look at a hydraulic gradient ratio. Or you can put it in a flexible wall permeameter, back pressure it to saturate it, and look at a hydraulic conductivity ratio. And the interpretation then becomes a little, well, we'll talk about the interpretation when we examine filter design. So folks, let me ask if there are any questions of clarification. I didn't think to invite you to jump in, but are there any questions of clarification on these, what I would call select material properties to inform filter design? And if you have any questions, please don't hesitate to ask. It's not the most exciting end of the course, trying to put across the principles of how we characterize or measure things. So I appreciate your hanging tight across these hydraulic properties. Going once, going twice. And if there aren't, let me turn it to filtration applications. I posted these notes, and I'm going to start with the very back end, if only because I think it's going to allow us to be nicely focused on where we want to get to, okay? So were I to take you, let me move these off and bring these principles of analysis and design for filter applications. And remember, please, culturally, we've moved from this convergence of the reinforced soil design and partial factors and mechanisms of analysis and very much a world of converging. Now in the world of filters, it's a very different scenario. If I turn to the back pages, I'm going to try and build the notes so that you too would be in a position to undertake a design and supervise construction and write the specification documents for the following. Okay. The challenge is the Alouette Dam. Okay. And the Alouette Dam, it doesn't have a generating station. Alouette Dam is one of these dams that holds it's like a saddle dam in essence. It holds the elevation of Alouette Lake, such that water from Alouette Lake flows at the far end of the lake through a tunnel and into a generating station and is used to generate power, not at the dam itself, but at a generating station that's actually quite far removed from the dam. And Alouette Dam was built in 1925-26. Completed in 28. My apologies. The Alouette Dam was built in about 1928. It was part of a sequence: Alouette, Stave Falls, and Ruskin. Have any of you ever been to Stave Falls? I appreciate if you're in Iran or if you're in Africa. Probably not. But
I grew up in Stave Falls.
Been to Stave Falls Dam?
I grew up there.
You grew up there, Alex?
Yeah.
It's a neat area. It's not that far from Vancouver. And I got to tell you, if Alouette Dam is a beautiful location, and if you get a chance and you want to break on and you're living locally to Vancouver, go out to Stave Falls. There's a fantastic museum there on the history of the hydroelectric development, and go visit the Alouette Dam. And you can look at the spillway that we will finish talking about. Okay, so if you're within striking distance of Vancouver, let me encourage you to do that. It's a nice day trip, actually. Go out with a bunch of friends. So now here's the deal. BC Hydro inherited Alouette Dam, and the spillway had erosion underneath the spillway. And that was dealt with in a number of ways. Finally, the decision was taken in the mid-1990s, actually early to mid-1990s, to pull out the old spillway and put in a new one. and in pulling out the old spillway and putting in the new one to put under drains underneath it. Okay, so were I to sketch things, and I'll do it somewhat crudely, okay, but it gives us a sense of the problem at heart here. Let's take a look at the cross section of the spillway. Okay, sitting on the ground. And over time, leaks in the spillway, let's give it a little bit of a, over time, leaks and joints in the spillway caused water to ingress and flow along and underneath the spillway. Arguably together with the presence of groundwater seepage itself. And so this under seepage beneath the spillway was eroding it. So it became a capital works to replace the spillway. And as a part of replacing the spillway, now I'm going to come back with, let's call this the old. And the old is dating back to the 1920s. And the new, which is dating back to about 1992, 93, if I remember correctly. With the new one, and I'll just show now the spillway and cross section. The decision was taken to put in an under drain okay, and the under drain is in combination with a filter. Okay, and then the original ground. So I'm going to call this the base soil or foundation soil, but because people talk about base filter compatibility, I'm going to call this the base soil. I'm going to call this the filter. And I'm going to call this the drain. In fact, it's an under drain to the spillway. So let's call this an under drain. Okay. And I take my hat off to the quality and foresight of the engineers at Hydro, and in particular, a colleague now retired at Hydro, or a friend at Hydro now retired, Steve Garner, who had the foresight to recognize, you know, when we bid this contract, or when the contractor bids the work, they may be able to place the under drain with relative ease and compact it, and place the filter with relative ease and compact it, such that we can achieve base filter compatibility. The under drain does its job, and we don't have unacceptable pore pressures building up during occasions on which the spillway is being used. nor do we have unacceptable inflows into it and or clogging of the drain and or erosion beneath it. In all likelihood, the contractor is going to be able to achieve this relatively easily with a granular filter. And a compacted under drain. But when we get onto the side slopes, the challenge of placing and compacting the granular filter and the challenge of placing and compacting the under drain is going to be considerable. And the foresight was, we doubt that the contractor is going to be able to achieve sufficient compaction to satisfy seismic design. And thus we need to examine the option of a geotextile filter. And it's uncommon for geotextile filters to be used in dam engineering. Dam owners tend not to like geosynthetics, unless they're in areas of the dam that can be accessed and rehabilitated. It's a relatively, although that's a weak descriptor these days, because geosynthetics has been around for some 50 odd years now, but a relatively new. I think it's more that if we can do it with sands and gravels, we will. So the question was, can we do this with a geotextile filter? Okay. And indeed, might we have to look at another form of drainage medium to go up behind the inclined cast in situ slabs of the spillway? Might we have to look at a geosynthetic underdrain? We don't know quite what it's going to be, so we won't give it a name other than another geosynthetic material. And the answer was, it turned out yes, a geotextile filter was used, and yes, a geosynthetic underdrain was used, because yes, the contractor wasn't able to satisfy placement and compaction requirements for granular filters and drains on a number of locations. So the spillway itself, and we'll go look at it in Google Earth, and we'll take a look at some pictures and materials and so on. All of the story of the rehabilitation of the Alouette Spillway Dam is described here, through to sending materials off for gradient ratio and hydraulic conductivity ratio testing. That's why I spent some time on those in the material properties. So that's where we're going to get to. But in order to get there, let's work our way through the principles of analysis and design. And I have some very clear learning objectives here. And it's to provide for you a framework for filter design according to modern practice for granular filters and geotextile filters. And I'm going to draw upon considerable experience from projects in doing this. Some of those projects are ongoing, and in fact, I have another dam review coming up in the new year for 2 dams actually in the US, and it's quite the topic, and there's been quite a bit done. And there's some very interesting both state of the practice testing that Hydro is currently sponsoring at PowerTech. I guess you could call it a Hydro subsidiary laboratory in Surrey. So if I were to make this more generic for the benefit of those outside of Canada, dam owners are now recognizing that likely internal erosion within dams is one of the biggest, if not
Sorry, Dr. Fanning, I'm not able to hear you.
Advanced design of granular filters, and also produced guide documents for design of geotextile filters from the dam engineering community, and that's what we're going to pursue. Now, before we do this, let me just go around the room, albeit as it's the electronic room, and let me just ask you if you've ever been engaged in filter designs, and was it for roads, or was it for dams or canals or mine waste, or? But let me just cast around and ask you. And the tiles appear in a certain order on my screen here. I'm not too sure if they do the same for you, but I'm gonna start in the top left. I'll give Amy a little heads up that you're in the top left, Amy. And then it's going to go Amy, Daniel, Alex, Tafsir, Taryn, Zara, Ryan, Zara, Grant, Jason, Meredith, and Emmanuel. And Amy, with those couple of seconds of warning, I turn it over to you, please.
Yeah, I've done a bit, not as much design, but a lot of just construction review of putting in geotextiles as a filter for like utilities.
Okay.
Or also we've done a couple creek rehabilitation where we've used filter materials, granular filter materials.
Yay. So, and did you have the chance to get out on site when some of those were being put in? Yeah.
Yeah.
So I will actually draw a little bit in the companion lecture next week. Draw a little bit from some of the resource access roads experience I have, just for getting it strong enough as well. Thank you, Amy, for that. Daniel, any opportunity you've had at all with geotextile filters?
Yep. Yeah. So a little bit. I've used filter cloths in retaining wall design. I've used some filtration for kind of temporary roads and access ways in soft soil sites and dense soil sites actually. Trying to think, and also same as Amy, utility installs, and then building envelope. We've used kind of your typical drainage mat, or wrapping a filter cloth around your gravel backfill.
Right. Yes, and if I pick up on both of those comments before moving on to Alex, I'd say that the world of filters, it has what I would describe as a lot of high frequency, small square meter applications. It's almost a default to put it in as a separator or a filter. I'm sure it'll do some good. Let's call those the world of high frequency, small magnitude jobs. And then when we get into waste containment facilities and mine waste sites, we get into relatively large magnitude, but they're relatively lower frequency. And a lot of the learning that we end up doing about geotextile filter design tends to be driven by the bigger projects with the bigger budgets, where the risks or consequences of failure are unacceptable and may lead to loss of life and or enormous costs to rehabilitate the failure. So that's why I've been intrigued to see it through the eyes of the dam engineering world, where it's not used as often as you might think, but when it is used, there's very careful consideration and budgetary allocation to make sure it's done correct. So we'll be trying to learn through the dams world and the waste containment facilities world. But what we're seeing applies across many more diverse applications. Continuing around the room, Alex?
Similar to Daniel, just drainage around homes and buildings and retaining walls. I've never done anything with anything larger than that for any dams or containment or anything like that.
And that's, I think that's consistent with the, these these bigger budget jobs don't come across or don't come along as frequently as the myriad of the highways and the resource access roads and the retaining walls and so on and so forth. Yeah. Tafsir. Okay. Yeah. Well, thank you. Nonetheless, it's I hear you, and I've stood in a gully while riprap has been pounding down onto a geotextile. It was interesting to come back a couple of years later to the same site and see what had happened to the geotextile over time in this relatively steep northwest creek. Taran, any experience?
I haven't personally designed it, but the company I work with, they did a really long soil nail wall, and they use behind the wall, they use I think it was Mira drain or some geocomposite, just to uh, uh, just to do drainage. And I think during installation, that drain system was covered with shotcrete and it didn't work, and finally end up putting actual drains in soil nail.
Right. Thank you. And Zara.
Yeah, I don't really have too much experience with geotextile filters, actually.
Okay, no, that's fine, and it's a variety. Ryan, over to you.
Yeah, actually, most of my filter design has been granular filters in tailings dams.
Yeah, okay, with the tailings, yeah. We will be touching on the granular filter, and I think it'll be interesting to compare some of the design guides that you may have turned to with the ones that I've certainly used quite extensively in dam engineering. And thank you for that, Ryan. Zara Masfei?
Sarah.
Sarah, thank you.
Yeah. Unfortunately, I don't have any experience of any decoration design.
Yeah, that's just fine. We all come at things from different backgrounds and experiences. Grant.
So yeah, I've done a little bit. Had one decent sized project where we actually used wick drains, vertical wick drains.
Oh yeah.
Up with the drainage, yeah, for a bridge going over a slough. So just to help the drainage go quicker.
Mm-hmm.
But I wasn't a part of the design team. I was just kind of out there watching. Can't really remember too much.
Yeah. I got involved evaluating geotextile filters as covers for wick drains, but actually on a tailings deposit to try and accelerate the drainage. And again, I'll draw a little bit upon that. The concern from the review team was that the geotextile might clog in attempting to dewater the mine waste tailings. And so we ended up putting quite a bit of effort into that and doing some testing actually here in the lab at UBC. But so interesting to learn of your wick drain experience, Grant. Jason?
Yeah, for me, similar to Ryan, the filter applications I've been involved with in earth structures have been primarily in granular material. I was just mainly construction monitoring.
Yep.
And any of the geotextile experience I've had with earth structures are mainly for barrier systems.
Okay.
So geosynthetic clay liners or geomembranes.
Okay. You know, I probably won't touch that much on GCLs or geosynthetic clay liners. I haven't really worked with them that much myself, but interesting to hear that you had done. And what kind of barrier application? What was the intent that the barrier was acting with? What was the project?
Yeah, so it was in the mining sector. So it was to hold back their tailings or their waste slurry.
Mm-hmm.
And this was in northern Canada, so it was in permafrost regions, so it was a frozen core dam.
Yeah.
So the core of the dam was saturated gravel that was mixed in an asphalt plant, and just wrapping around the core of this frozen core, they used a GCL.
Okay. Thank you, Jason. Thank you. And Meredith, and then we'll finish with Emmanuel, but Meredith, please.
So my experience is predominantly for tailings dam design, and I've been involved in both granular and geotextile design.
Okay.
Predominantly just like wrapping granular filters for like finger and toe drains underneath embankment raises or buttresses. And then I've also done a little bit of geomembrane design for a spillway.
Mm-hmm. Okay, interesting. And we'll touch a little bit on kind of the philosophy and upside and downsides of wrapping drains and relatively small. It is a philosophy that's come out of municipal solid waste on how to give your filters the best chance of working over their entire service life. But thank you for that, Meredith. And finally, Emmanuel, do you have any experience that you'd like to share with us?
Well, we don't use geotextile in Nigeria to a certain extent. We use Godula a lot, but I've not been involved in one personally. But we use Godula, not geotextile.
Sure.
Geotextile is a bit expensive, so we don't use it.
Yes. Yeah. No. Depending on where we are in the world and relative cost of materials, sometimes it's not an economic option to select, and I appreciate that. Very good. Thank you for that. I get a sense that a lot of it's in highways, retaining walls, and or mine waste tailings. And let me give you a sense of what I mean by trying to combine this appreciation for granular and geotextile filters. And this is part of setting up almost the culture into which I'll convey what I think is a nice framework for taking and defending decisions. And I'm going to do it with regard to the homework assignment number 2, which I'm going to release today. I haven't thought about when is a good time to hand it in. It's certainly not in the next couple of weeks, so don't worry about that. I want to hand it out so that we actually have it as a resource to refer to as a part of the teaching. And it's going to be an earth dam filter design, but I ask that you look at it from a granular filter as well as a geotextile filter perspective. And these are real data. They come from another dam. The dam was actually decommissioned. So the only dam that BC Hydro has taken out of its asset base, to the best of my knowledge. And it did that because of unacceptable sinkhole activity. And the concern was that a filter had not been put in a cut-off trench at the time of construction. Hydro didn't build the dam. They didn't design it. They didn't build it. They inherited it as an asset swap and pretty much knew from the get-go that it was a problematic asset to have inherited. In essence, the lower core of the dam, this is the number 200 sieve here. Okay, so the lower core of the dam, which is really a till material, quite broadly graded, was in contact in the cutoff trench with a foundation unit. And the foundation unit was in essence the nominal filter to the core. But that foundation unit doesn't actually satisfy modern filter design criteria. And notwithstanding several efforts to upgrade and work with the dam, in the end, BC Hydro took the decision to decommission the dam. It was Curzere Dam, which is south of Revelstoke and up in an alpine valley. So that's the nature of the problem. Were a filter to have been designed to modern design practice, the dam was built, if I remember correctly, in about 50, 60 years ago. Modern design practice would call for a granular filter that looks like this. And so in this second homework assignment, I provide you with these data here. And I ask you, modern design practice, and I'll ask you to go through with reference to modern design practice. I will choose this. Ryan and Meredith, if you've had opportunity, and I'm working from memory if others have to, is this the design approach that you would have used for granular filters, or in either the country or jurisdiction where you were working, was it a different design guide? This is the so-called Chapter 26, which would be the default design guide for granular filters in dam engineering. But Ryan, Meredith, is this one that you would have used, or is this a new one for you guys?
Yeah, I think it's a similar one. I think from memory, we looked at quite a few from like USBR, USACE.
Yeah.
There's a third one, I can't remember from memory.
Yeah.
We kind of did the design using all three, and then kind of ended up choosing the most appropriate, I think.
Yeah, that sounds about right. And Meredith?
Yeah, similar to Ryan, I think we also assessed an ICOLD document.
Oh, yes. It might even have been drawing upon the ICOLD bulletin on internal erosion. Yeah, the bulletin 164 that's come out recently as well. And all of these things that, they all chase back to kind of empirical origins, and in many cases chase back to Sherrard and work by Sherrard, and subsequently that work by Foster and Fell. So what I ask you to do is to check. The granular filter is specified with regard to 7 control points in this particular document. It's a US document. And those 7 control points for the granular filter would be these ones: 1, 2, 3, 4, 5, 6, and 7. And they serve various purposes: limiting maximum particle sizes for segregation, limiting fines content for cracking, soil retention and hydraulic permeability criterion. And then you don't want the range here to be too broad, otherwise you can get gap graded soils, so you adjust it a little bit. So there's a number of practical things that are going on, and so I ask you to note the 7 control points, but with regard to one of them, which is actually going to turn out to be this one, the D15 of the filter is the surrogate to permit for soil retention. And I ask you, and I'll point you in directions. I ask you to look at the literature. I'm going to post this assignment later today. I ask you to look at the literature and cite the evidence in support of the design criterion that was used here. In other words, it's fine for me to use this design guide, but where the heck do the rules of the design guide come from? And thus, in a world of empiricism, is it appropriate for me to be using this in my project? And I'm focusing on dam engineering here. So that's the first part. The first part is intended to understand the origins of empirical design criteria for granular filters, and to do so with regard to soil retention. And when you find the evidence and the origins, and that's going to be in journal articles, in ASC, amongst others, I ask you to list the strengths and weaknesses of the evidence that you find and comment upon the conservatism or otherwise of this base soil retention criteria. So we need to understand granular filter, and we'll go through that. And then you've been asked to recommend a geotextile filter as an alternative. And so I send you in the direction of the US Bureau of Reclamation, USBR. I send you in the direction of this document, embankment dams, geotextiles. And I ask you to select a geotextile product as they would direct you to do that. And they, in turn, embedded in their design guidance, they use a geotextile filter design guide that has some absolutely sterling origins in terms of geosyntech consultants out of the US. And Giroux is a very knowledgeable individual. Scott Lutich, who ran the lab there, was a very, very astute materials-oriented kind of guy. And that's embedded in the reclamation guide. So I ask you to look at speccing a geotextile according to US Bureau. But if we want to have confidence, how much confidence do we have in these empirical rules? So it's a little bit like the empirical rules for granular filters. How much confidence do we have in the empirical rules for geotextile filters? So I ask you to go to a bunch of data published by Jean Lafleur in the Geotextiles and Geomembranes. And he reports data for 8 geotextiles and a bunch of soils. So I ask you, on the matter of the soil retention criteria for the geotextile filter, just as I ask you for the soil retention criteria for the granular filters, let's actually see. Let's just see what kind of a match are we getting between the lab data of Lafleur and the design guide of Lutich. And do you believe these data? If you do, does it support the design guide? How is that going to influence the way you think? So this first part is granular filters, and this second part is geotextile filters. And then the third part of the assignment is to ask you to compare. If you were going to test a granular filter, you'd probably check the granular filter compatibility using the Foster-Fell, and this will also take us back, Meredith, to the ICO Bulletin 164. You'd probably go back to Foster and Fell's 2001 document, ASCE, assessing filters that don't satisfy design criteria. And if we go in here, we discover, wow, look at that. We're going to have a rigid wall permeameter, and we're going to be putting the soil against the filter. In this case, it's a granular filter. And we're going to check, is it compatible or not? So if you had to check it, contrast the basis for checking a granular filter by lab testing. And I ask you to contrast the basis for the interpretation of the granular filter versus the basis for a geotextile filter. And this one is our gradient ratio test, which I went through in a little bit of detail today. And this one is the hydraulic conductivity ratio test. In other words, in a nutshell, hey, become familiar, please, with soil retention empirical criteria for granular filters and their origins. Become familiar with soil retention and speccing a geotextile filter, but understand the origins of the empirical rules. And then, were you on a project? It would be a big project. Then how would you test the compatibility of a granular filter, and how would you test the compatibility of a geotextile filter? And do we do it in the same way? Do we expect the same things? Do we apply the same set of rules for granular filters and geotextile filters when we want to evaluate them for a project? that's being done right now, actually. In fact, Mark Foster and I are working with a dam owner right now and on evaluating granular filters for a dam. So there's lots of, you know, the learning objectives here, and I'll close at this point. The learning objectives here are very much to influence the way you think about what you do, okay? To enable you to take and defend decisions with confidence. And I'll point you towards empirical design guidance, but I would like you to think independently about how you would pick up that guidance and use it. And then if you had to embark on elements of testing to verify a design recommendation, what tools or techniques, what test methods, and how might we interpret them? So that's the learning objective, or the nature of that's the culture of this deliverable. And it's a different culture to the deliverable on the reinforced soil assignment. Please see this change in culture that we're going through from the first half of the course to the second half of the course. So it's informed by this that we will complete our work on the filter applications, and I'll be primarily looking at geotextiles, but I want to have this companion world of the granular filters, and that's where we're going to be headed in the lecture next week. So if there are any, I'm going to stop the recording now. Actually, let me just take care of that.